In any collision, momentum is conserved. There are some special instances where a conservation of kinetic energy also occurs. These are called elastic collisions. So the total kinetic energy of the system before the collision is the same as the total kinetic energy of the system after the collision. Now, completely elastic collisions are not very common on the macroscopic scale. Billiard balls and bumper cars are two examples, but that's really about as close as you're going to get. Elastic collisions are more common at the atomic level, where atoms and molecules are colliding. They are called elastic collisions because for a tiny moment, when two objects are in contact, there is energy stored as elastic potential energy. Look at two blocks here. They are moving along a frictionless surface, so there is no net force acting on either one of them. The first block has some kinetic energy associated with it, and we can call Ke1. The second block also has some kinetic energy associated with it, and we can call that Ke2. If we define our system as the two blocks, then the total kinetic energy of the system is the kinetic energy of 1 plus the kinetic energy of 2. After a collision, the two blocks bounce off of each other and move off in opposite directions. They each now have a new kinetic energy associated with them. We refer to these new kinetic energies as Ke'1 and Ke'2. The total kinetic energy of the system is still the two kinetic energies added together, or Ke'1 plus Ke'2. Since kinetic energy is conserved, the sum of the kinetic energies before the collision is equal to the sum of the kinetic energies after the collision. Of course, we can rewrite this into something a little more useful. Now I'm going to point out that there are a lot of 1s and 2s in that very small space. You might imagine this can get a little confusing when writing things down, especially if you don't have the best handwriting. So we're going to rename our blocks. Instead of block 1, we are going to call it block A, and block 2 will now become block B. Now you just may be looking at this and thinking that doesn't help at all. That's okay. Remember also that momentum is conserved in this collision. So the sum of the momentums of A and B before the collision is equal to the sum of the momentums after the collision. Again, we can write this out with our equation for momentum. So at the top we have an expression for the conservation of momentum. At the bottom we have an expression for the conservation of kinetic energy, both during an elastic collision. What's nice about this is these two equations describe different things, but use the same two variables to do it. So let's play with this a little bit and see what we can come up with. At this point we have two objects, A and B, and they are both moving and eventually collide elastically with each other. First, let's move it around a little bit, so all of the stuff A is on the same side, and all of the stuff for B is on the other side. For now, let's assume that the masses do not change. That lets us pull the masses out of each expression and simplify it a little bit. Now we can do the same thing with our kinetic energy conservation. Move the A's and the B's over the same side. And since there's a half in each one of those expressions, we can pull those out and get rid of them. And again, since our masses don't change, we can pull the mass out and get a simplified expression that describes the conservation of kinetic energy in an elastic collision. Now you might notice that we can actually factor a couple of those terms. VA squared minus VA prime squared becomes the quantity VA minus VA prime times the quantity VA plus VA prime. We can do the same thing on the V side. But why would we want to? Well, part of this equation is the same as the equation we ended up with in our rewritten momentum expression. But again, why do we care? Math people might hint to us that if we were to divide the momentum expression by the kinetic energy expression, we will get something even simpler. We get the sum of A velocities equal to the sum of the B velocities. Of course, we can also rearrange in terms of before and after the collision. Or, if you're big on symmetry of numbers, you can write it this way. All three of these are the same equation. And interesting because that last one there tells us that the speed of the two objects after an elastic collision has the same magnitude but opposite direction than before the collision. So let's apply this a little bit. We have a billiard ball A with a mass of m that moves with a speed of VA. It collides head-on with a billiard ball B, also with mass m, moving at velocity b. What are the speeds of both balls if the collision is elastic? We know that in a collision, momentum is conserved, so we can start with our momentum conservation equation. From the problem, we know that the mass of ball A and the mass of ball B are the same. This is helpful because this lets us completely get rid of the masses in our equation. We're trying to find the final speed of both A and B, so that unfortunately leaves us with two unknown variables in our equation. Never a good thing, but remember, we do have another equation that deals with these same variables. Remember, an elastic collision is one where kinetic energy is conserved. So we can also use our newly written expression from our kinetic energy relationship. All we really need to do is add these two equations together. When we do this, on the left we have two VAs, and the VB terms subtract each other out. On the right we have two VB primes, and the VA primes subtract out. This simplifies down to 2VA equal to 2VB prime. Of course we can divide out those two since there's one on each side. So all of that, and we find that the initial velocity of A is equal to the final velocity of B. Even more interestingly, we could also go back and subtract those two equations. This gives us a final expression of the initial velocity of ball B equal to the final velocity of ball A. So what's happening here? The two balls with their own beginning velocities collide in an elastic collision, and all that really happens is they switch velocities. Now, something to keep in mind, this is only true because they both have the same mass. Now, what happens if we have the same situation, but ball B starts out at rest? We can go through all the same math, adding and then subtracting the conservation equations for momentum and kinetic energy. The only difference is that when we get to the end, we know the initial velocity of B is equal to the final velocity of A. So both of those are equal to 0. You've probably observed this if you've ever watched or played a game of pool. As long as the two balls have the same mass and the ball is hit straight on with no extra spin, you would be able to measure the change in velocities in both balls. And you would find that they just switch those velocities. Now what happens if the masses are not the same? Say we have a proton with a mass of 1.01 atomic mass units traveling with a speed of 3.60 times 10 to the 4th meters per second. It has an elastic head-on collision with a helium nucleus with a mass of 4.00 atomic mass units. So what are the velocities of both particles after the collision? Again, let's start with conservation of momentum. We can start out by getting rid of that second term since helium starts out at rest. We do still have two variables, but since it's an elastic collision, kinetic energy is also conserved. So we can use that simplified equation to find some things. Again, the initial velocity of the helium is 0, so let's just get rid of that right away. Then we can rearrange for VA prime. We could do VB prime, it doesn't really matter. Our goal is to plug this into our momentum equation. When we do that, we get a nice expression that can be multiplied out. Now we have some like terms and we want to move those around a little bit. Now our goal here is to get VB prime by itself. That's one of the things that we're looking for. And we can start by moving the MAVA term over to the left, giving us two of those over on that side. Then we can pull out the VB prime out of both of our terms on the right and rearrange to solve for the final velocity of the B particle. From here, it's just a matter of plugging in our knowns to find the new velocity of the helium particle to be 1.45 times 10 to the 4th meters per second. Now we know the final velocity of 1, we can use our kinetic energy conservation expression to find the velocity of the proton to be negative 2.15 times 10 to the 4th meters per second. This result makes sense if you think about the proton bouncing straight backwards in the opposite direction, but with a slightly smaller velocity. So in elastic collisions, we know that momentum is always conserved in any collision. The total energy is also conserved in a collision. Both of those are always true. But in a perfectly elastic collision, the kinetic energy before the collision is the same as the kinetic energy after the collision.